Okay, so let's focus on this word. What's a generation?
Every 20 years or something.
In humans, yes. A generation is how long it takes a species to have babies and have those babies mature. So from the time of birth to maturity. So in humans, we very often say like, oh, a generation is about 20 years. Because on average, though actually the average age for first childbearing in the U.S. is now like 26. But yeah, okay, 20 years, give or take. In rats, how long is the generation? A couple weeks, yeah, a week. You know, during normal times, maybe it's 3 or 4 weeks. During this, it's like 2 weeks. So after only a few generations, is the population increasing rapidly in the course of a month? Yeah, so this fits perfectly. It assumes that, now, this is a little bit off, assumes that birth and death rates remain constant no matter how large the population gets. In this case, you've got kind of a special circumstance. Is the birth rate remaining constant? The birth rate's actually increasing here. So it's not quite spot on with that. Up to the point when the bamboo fruit is all gone and the rice crop is all in, is the death rate remaining constant? When there are plenty of calories available for rats. Yeah, the rats are not, when there are plenty of calories for them, either from bamboo fruit or from rice, they're not dying young. They're living a full, healthy life, and I mean, gosh, they're reproducing like crazy. So this is that J-curve growth. It looks like a J. Can anything go up forever? So typically what we talk about, and this isn't shown in this exponential growth model, but at the end, there's almost always, whoomp. So it's like this. Whoomp. That drop at the end is a crash. That's a population crash. Because exponential growth just isn't sustainable. You just can't keep putting more individuals into the environment. You can't keep pulling more calories out of the environment. Okay. So here's the thing about exponential growth. This doesn't usually happen in nature. Do you think the rats and Mautam are a bit of an exception? Yeah. It's kind of an exceptional thing. This is something that happens, what, every 50 years roughly, every 48 years. This is not an everyday occurrence. When it does happen, there's usually a price to pay at the end. So you typically will see, you know, J-curve growth, boom, followed by a crash in population size. Eventually, a population that's getting bigger and bigger and bigger and bigger and bigger and bigger and bigger runs out of food, runs out of space, runs out of, you know, everything they need, and on top of it, drowns in their own waste. How's that for a lovely image? So one of the classic examples is if you put a bunch of bacteria in a laboratory dish. Though, you know, if the conditions are good, you've got a nice rich agar medium for them to grow on, you've got nice temperatures for them, they'll reproduce like crazy. And their population will go whoop, until the point at which they eat themselves out of house and home, and their cellular wastes make the whole place so disgusting they can't live there, and then the population just crashes. So what would be another example of exponential growth that you could write down on here? I know one that I'm thinking of. It seems like I've just heard something about rats. That's it. Oh, wait, you didn't say rats. I'm sorry. Rabbits. Okay. But I think rats during Mautam are another really good example. We'll talk about rabbits because that's a great one. And this is specifically black rats. And Mautam is spelled M-A-U-T-A-M. Okay, Rabbits, where did we talk about rabbits having an exponential growth? Australia. Whew. I hate it when it does that. So this doesn't happen very often. It doesn't usually happen without something sort of exceptional happening. Eventually it becomes limited, but it takes a long time. During this whole buildup here, do some different color, nothing is limiting their growth. There are no limits during that period of rapid growth. They finally run up against a limit at the point when they're crashing. Okay? So for rats, what becomes the limiting factor?
Amount of food.
Yeah, the amount of food. The actual number of calories that are available in the environment. Calories are energy. We don't think about that very often. Maybe if you're wrestling and you're starving yourself, you do. But calories are literally, your body is, it's like putting wood on a wood stove. Your body's literally burning food for energy. It's like shoveling coal onto a locomotive. And there's a limit to the amount of energy that's out there in the environment. And so for these rats, you know, at the point when the calories run out, their population crashes. Tomorrow we will have a quick recall quiz on exponential growth, and especially as it's related to the film. A little 3-question quiz. And we'll start talking about how things more often really look in wild populations. Oh, by the way, I did get an email back from Division of Wildlife, finally. A very nice young man who is a customer service specialist. He has a bachelor's degree in wildlife management, and we'll talk tomorrow. Have a good day, folks.